For thousands of years, humanity believed matter was simple: stone, metal, water, fire, something solid, something understandable. But hidden deep inside every atom was a force powerful enough to light the stars or destroy entire cities. Nuclear physics changed the course of civilization forever. It gave humanity electricity from the heart of matter. It helped reveal the age of the universe. It created revolutionary medical technologies. And it also created the most destructive weapons ever built. This is the story of the scientists who unlocked the atom, the discoveries that transformed modern science, the wars that accelerated nuclear research, and the terrifying power humanity learned to control. This is the history of nuclear physics. The journey into nuclear physics began long before laboratories, particle accelerators, or modern science. More than 2,000 years ago, ancient philosophers asked a simple question: what is everything made of? In ancient Greece, philosopher Democritus proposed that all matter was made from tiny, indivisible particles. He called them atomos, meaning uncuttable. At the time, it was only philosophy. There was no proof, no experiments, no mathematics. For centuries, the idea remained little more than speculation. During the Middle Ages, alchemists searched for mystical ways to transform matter. They dreamed of turning lead into gold, but without realizing it, they were laying the foundations of chemistry. By the 17th and 18th centuries, science began replacing superstition. Scientists learned how gases behaved, how elements reacted, how matter could be measured. Then, in the early 1800s, English chemist John Dalton revived atomic theory. He proposed that every element consisted of unique atoms. For the first time, atoms became part of real scientific thinking. But scientists still believed atoms were solid spheres, tiny billiard balls, indivisible, unbreakable. They had no idea that deep inside the atom, an entirely new universe existed. In the late 19th century, electricity fascinated scientists around the world. Researchers experimented with mysterious glowing tubes called cathode ray tubes. Inside them, invisible rays traveled between metal electrodes. Most scientists did not understand what these rays were. Then, in 1897, British physicist J. Thompson made a revolutionary discovery. The rays were made of tiny, negatively charged particles smaller than atoms. Thompson had discovered the electron. The atom was no longer indivisible. This discovery shocked the scientific world. If atoms contained smaller particles, then atoms themselves had structure. Thompson imagined the atom like a plum pudding, electrons embedded inside a positively charged sphere. It was wrong, but it was the first serious model of atomic structure. For the first time in history, humanity had opened the atom, and soon scientists would discover something even stranger hidden inside. In 1895, German scientist Wilhelm Röntgen discovered X-rays, invisible radiation capable of passing through human flesh. The discovery stunned the world. 1 year later, French physicist Henri Becquerel investigated whether glowing materials produced similar rays. While studying uranium salts, he made a surprising observation. Even without sunlight, uranium emitted invisible radiation. The energy came from the atom itself. This mysterious phenomenon became known as radioactivity. Soon, two brilliant scientists would dedicate their lives to studying it: Marie Curie and Pierre Curie. Working in primitive laboratory conditions, the Curies isolated new radioactive elements, polonium and radium. The work was exhausting and dangerous. At the time, scientists did not understand radiation's deadly effects. Marie Curie often carried radioactive samples in her pockets. She described the glowing tubes as beautiful, but prolonged exposure slowly damaged her health. Still, the discoveries transformed science forever. Radioactivity revealed that atoms were not stable. They could change, decay, transform into other elements. The atom was alive with energy, and scientists were only beginning to understand how much energy existed inside it. By the early 1900s, scientists knew atoms contained electrons, but they still did not understand how those electrons were arranged. Then came one of the most important experiments in scientific history. In 1909, physicist Ernest Rutherford and his team fired alpha particles at an ultra-thin sheet of gold foil. According to existing theories, the particles should pass through with only slight deflection. Most did, but some bounced backward. Rutherford was stunned. He later said it was like firing a cannon shell at tissue paper, only for the shell to bounce back. The results revealed something extraordinary. Almost all the atom's mass was concentrated in a tiny central core, the nucleus. Electrons orbited around this dense center. The modern nuclear atom had been discovered. This breakthrough gave birth to nuclear physics. Scientists now understood that the nucleus held enormous power, but they still did not know what the nucleus was made of. As scientists explored atomic structure, classical physics began to fail. Atoms did not behave according to ordinary rules. Electrons could jump between energy levels. Light behaved like particles. Particles behaved like waves. A new theory emerged: quantum mechanics. Scientists like Max Planck, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger transformed modern physics. Niels Bohr proposed that electrons orbited the nucleus in specific energy levels. When electrons moved between levels, atoms emitted light. Quantum theory explained atomic behavior with extraordinary accuracy. But quantum mechanics also revealed something unsettling. At the smallest scales, reality itself became uncertain. Particles existed in probabilities. Events could not always be predicted. The universe was stranger than anyone imagined, and understanding the nucleus would require embracing this strange new physics. Scientists soon identified the positively charged particle inside the nucleus, the proton. But something still did not make sense. The mass of atoms was too large to be explained by protons alone. Another particle had to exist. In 1932, British physicist James Chadwick discovered the neutron. Unlike the proton, the neutron carried no electric charge. This discovery completed the basic structure of the atom. Atoms contained protons, neutrons, and electrons. The neutron proved especially important because without electric charge it could penetrate atomic nuclei more easily. That made it the perfect tool for nuclear experiments. And within just a few years, neutrons would unlock the most powerful reaction humanity had ever discovered. In the 1930s, scientists bombarded uranium atoms with neutrons. They expected small changes. Instead, they discovered something astonishing. The uranium nucleus split apart. This process became known as nuclear fission. When the nucleus split, it released enormous energy and additional neutrons. Those neutrons could split more atoms, creating a chain reaction. Physicists Lisa Meitner and Otto Frisch correctly explained the process. The implications were terrifying. A controlled chain reaction could produce immense power. An uncontrolled chain reaction could create a bomb unlike anything in human history. As Europe moved toward war, governments realized nuclear physics had become a matter of survival. In 1939, physicist Albert Einstein signed a letter warning the United States government that Nazi Germany might develop atomic weapons. The warning changed history. The United States launched the Manhattan Project, a massive secret program involving thousands of scientists, engineers, and workers. At sites across America, researchers raced to build the world's first atomic bomb. The project gathered some of the greatest scientific minds of the century: J. Robert Oppenheimer, Enrico Fermi, Richard Feynman, Niels Bohr, and many others. At Chicago, Enrico Fermi created the first controlled nuclear chain reaction. Humanity had successfully released nuclear energy. Meanwhile, at Los Alamos, scientists designed two terrifying weapons: a uranium bomb and a plutonium bomb. On July 16, 1945, in the New Mexico desert, the first nuclear explosion in history lit the sky. The Trinity test. Witnesses described a blinding flash brighter than the sun, a rising fireball, a shockwave that shook the earth. Oppenheimer later recalled words from the Bhagavad Gita, "Now I am become death, the destroyer of worlds." The nuclear age had begun. In August 1945, the United States dropped atomic bombs on the Japanese cities of Hiroshima and Nagasaki. The destruction was absolute. Thousands died instantly, and many more from radiation sickness in the months and years that followed. These events forced a Japanese surrender, ending World War II. But they also confronted humanity with the devastating reality of nuclear warfare. The survivors, known as hibakusha, would carry the physical and emotional scars of the atomic age for the rest of their lives. The world had entered a new, uncertain era, a time where the power to destroy entire civilizations was now a permanent reality. After World War II, nuclear physics became central to global politics. The United States and the Soviet Union entered a dangerous competition. The Cold War. Both nations rapidly expanded their nuclear arsenals. Scientists developed hydrogen bombs far more powerful than the weapons dropped on Japan. These thermonuclear weapons used nuclear fusion, the same process powering the sun. The explosions were almost unimaginable. In 1961, the Soviet Union tested the Tsar Bomba, the largest nuclear weapon ever detonated. Its blast shattered windows hundreds of kilometers away. As nuclear stockpiles grew, the world lived under constant threat. The doctrine became known as mutually assured destruction. If nuclear war began, both sides would be annihilated. The Cuban Missile Crisis of 1962 brought humanity dangerously close to global nuclear conflict. For 13 days, the world stood at the edge of catastrophe. Fortunately, war was avoided. But the fear of nuclear annihilation shaped an entire generation. While nuclear weapons terrified the world, scientists also saw peaceful possibilities. Controlled nuclear reactions could generate electricity. Nuclear power plants used fission to produce heat. That heat created steam. Steam powered turbines, and turbines generated electricity. Nuclear energy offered enormous advantages. A small amount of fuel could produce massive amounts of power. And unlike fossil fuels, nuclear plants produced very little carbon dioxide during operation. Many countries embraced nuclear power: France, the United States, Russia, Japan, and others. But nuclear energy also carried serious risks. Accidents at 3 Mile Island, Chernobyl, and Fukushima revealed how dangerous reactor failures could become. The 1986 Chernobyl disaster released massive radiation into the environment. Entire towns were abandoned. It became one of the worst technological disasters in history. The debate over nuclear power continues. Some view it as essential for reducing climate change. Others fear the risks remain too great. Despite its association with war, nuclear physics has also saved millions of lives. Radioactive isotopes transformed medicine, allowing for the precise detection and treatment of diseases. Doctors used nuclear imaging techniques to study organs, blood flow, and disease. PET scans allow physicians to detect cancer and neurological disorders. Radiation therapy destroys cancer cells with remarkable precision. Nuclear physics also sterilizes medical equipment and helps scientists understand biological processes. Today, hospitals around the world rely on technologies born from nuclear research. The same science that created atomic bombs also became a powerful tool for healing. As nuclear physics advanced, scientists built increasingly powerful machines to explore matter, particle accelerators. These massive instruments accelerate particles to extraordinary speeds before smashing them together. By studying the debris, physicists uncover the hidden structure of reality. At CERN, near the border of France and Switzerland, the Large Hadron Collider became the world's largest scientific machine. In 2012, researchers confirmed the existence of the Higgs boson, a particle linked to the origin of mass. Modern nuclear and particle physics continue exploring profound mysteries. What is dark matter? Why does the universe exist? What happened moments after the Big Bang? The quest that began with ancient philosophers continues today. The history of nuclear physics is the story of our journey to the very heart of existence. While nuclear fission splits atoms apart, fusion combines atomic nuclei. Fusion powers the stars. Scientists have spent decades trying to recreate that process on Earth. If successful, fusion could provide nearly limitless clean energy. But controlling fusion is incredibly difficult. Temperatures must exceed millions of degrees, plasma must remain stable, and reactors must produce more energy than they consume. Projects like ITER aim to make fusion practical. Some scientists believe fusion could transform civilization. Others warn that major engineering challenges remain. Still, the dream continues, to harness the power of the stars themselves. Nuclear physics forced humanity to confront difficult ethical questions. Should scientific knowledge ever be restricted? Were the atomic bombings justified? Can nuclear weapons prevent war? Or do they threaten human survival? Many scientists struggled with guilt after World War II. Some became activists for arms control and nuclear disarmament. Treaties attempted to limit nuclear proliferation, yet nuclear weapons remain in global arsenals today. At the same time, nuclear science continues benefiting humanity through energy, medicine, and research. The story of nuclear physics is not simply a story about atoms. It is a story about power, responsibility, fear, and human ambition. The history of nuclear physics is often told through famous male scientists, but many of the field's greatest breakthroughs came from extraordinary women whose contributions changed science forever. Marie Curie became the first person to win 2 Nobel Prizes. Her research on radioactivity transformed modern physics and medicine, yet she worked in harsh conditions with little protection from radiation. Lise Meitner helped explain nuclear fission. Despite her critical role, she was overlooked when the Nobel Prize was awarded. Physicist Chen-Xiong Wu conducted groundbreaking experiments that overturned long-standing assumptions in physics. Her work proved that nature itself did not always behave symmetrically. Throughout the 20th century, women in nuclear science often faced discrimination, exclusion, and limited recognition. Yet their discoveries became essential to modern physics. Today, scientists around the world continue building on their legacy. Nuclear technology promised incredible power, but when systems failed, the consequences could be catastrophic. In 1979, the 3 Mile Island accident in the United States triggered fear across the world. Although the damage was limited, public confidence in nuclear energy declined. Then came Chernobyl. On April 26, 1986, reactor number 4 exploded at the Chernobyl nuclear power plant in Soviet Ukraine. A flawed reactor design and human error caused the worst nuclear disaster in history. Radiation spread across Europe. Entire communities were evacuated forever. Firefighters and workers risked their lives to contain the disaster. Many suffered deadly radiation exposure. Decades later, the exclusion zone remains largely abandoned. In 2011, another crisis struck. A massive earthquake and tsunami hit Japan, damaging the Fukushima Daiichi nuclear plant. Hydrogen explosions rocked the facility. Large evacuations followed. These disasters reshaped global attitudes toward nuclear energy. Some nations reduced nuclear programs. Others strengthened safety systems. The accidents became stark reminders that nuclear technology demands extreme caution. Nuclear physics did not remain confined to Earth. It also helped humanity explore the cosmos. Many spacecraft rely on radioisotope thermoelectric generators. These systems convert heat from radioactive decay into electricity. They power missions far from the sun, where solar panels become ineffective. The Voyager probes, launched in 1977, continue sending data from interstellar space thanks to nuclear power. The Curiosity and Perseverance rovers on Mars also depend on nuclear energy. Scientists have even proposed nuclear-powered rockets capable of reaching distant planets more quickly. One day, nuclear propulsion may help humans travel deeper into space than ever before. The atom that transformed life on Earth may also carry humanity to the stars. Modern nuclear physics faces mysteries more profound than ever. Astronomers discovered that visible matter makes up only a small fraction of the universe. Most of the cosmos appears to consist of invisible material, dark matter. Scientists cannot see it directly, but they observe its gravitational effects on galaxies and cosmic structures. Deep underground laboratories search for rare particle interactions. Massive detectors filled with liquid xenon wait silently for evidence. Particle accelerators attempt to create unknown particles. So far, dark matter remains one of science's greatest unsolved mysteries. The answer may completely transform our understanding of reality. The atomic age changed human civilization forever. Nuclear physics reshaped warfare, industry, medicine, energy, and our understanding of the universe. Its discoveries revealed that unimaginable energy exists within matter itself. But the history of nuclear physics is not only a scientific story, it is a human story, a story of curiosity, competition, cooperation, fear, and hope. The atom became both a symbol of progress and a warning about humanity's power. Future generations will decide how nuclear science continues to shape the world, whether as a source of destruction or a tool for exploration, medicine, and clean energy. The nucleus remains one of nature's greatest secrets, and humanity's journey into the atomic world continues. As nuclear weapons transformed global power, secrecy became critical. Governments guarded atomic research with extreme security, but secrets rarely remain hidden forever. During World War II and the Cold War, spies infiltrated nuclear programs. Some scientists secretly passed information to the Soviet Union. Klaus Fuchs, a physicist working on the Manhattan Project, provided vital atomic information to Soviet intelligence. The balance of global power changed rapidly. In 1949, the Soviet Union successfully detonated its first atomic bomb. The American nuclear monopoly had ended. Soon, Britain, France, China, and other nations developed nuclear weapons. The world entered an era where information itself became as dangerous as the weapons. Nuclear espionage intensified distrust between nations. Radiation is one of the most misunderstood forces in nature. It cannot be seen, smelled, or touched. Yet, in various forms, it surrounds us constantly. Radiation flows from deep space as cosmic rays. It emanates from the rocks beneath our feet, from the very Earth itself, and even from within the human body. The birth of nuclear physics revealed that radiation exists in different, distinct forms. Alpha particles, which are heavy and easily blocked. Beta particles, smaller and faster. And gamma rays, powerful bursts of electromagnetic energy. Gamma rays can penetrate almost anything. Each of these behaves differently. Each carries unique levels of energy. Each carries different levels of potential danger. In small, controlled doses, radiation became an essential tool for human progress. It allowed us to peer inside the human body without surgery and carbon date the relics of our ancient past. But we also learned the hard way that high exposure is devastating. It can damage living cells and alter DNA. High exposure can cause deadly radiation sickness. Still, the study of radiation transformed both biology and medicine. It also forced humanity to develop strict safety standards. Today, radiation monitoring is a silent guardian in our lives. Monitoring exists in our hospitals, research laboratories, international airports, and nuclear facilities around the globe. Beyond medicine, radiation plays a vital role. It helps us ensure the safety of our food and powers the smoke detectors in our homes. In industry, it allows engineers to detect hidden flaws in metal structures, ensuring the safety of bridges and aircraft. Scientists continue to study radiation to unlock the secrets of the early universe, looking back billions of years to the origin of everything. By observing the radiation left over from the Big Bang, we can look back to the very beginning. From the electronics needed for deep space travel to the therapies of tomorrow, we are constantly refining our understanding. Invisible though it may be, radiation remains one of the defining discoveries of nuclear science. a force we have learned to respect and use for the benefit of all. Nuclear physics reshaped military strategy not only through bombs, but through propulsion. For decades, submarines were limited by their engines, forced to surface frequently to recharge batteries or draw in air. But in the 1950s, a revolution began: the development of the nuclear-powered submarine. Inside these vessels, a compact nuclear reactor provided a nearly inexhaustible source of energy. Unlike conventional submarines, these new vessels could remain submerged for months, traveling at high speeds without ever needing to surface. The USS Nautilus became the world's first operational nuclear submarine, marking a new era of naval warfare. In 1958, it accomplished the unthinkable, crossing beneath the North Pole. Its captain sent the legendary signal, "Underway on nuclear power." The success of the Nautilus changed everything. Soon, massive nuclear reactors were powering aircraft carriers like the USS Enterprise. This allowed entire fleets to project power across the globe without the need for frequent refueling. But it was beneath the waves that the most significant shift occurred. Nuclear submarines became the ultimate silent guardians of the Cold War. Equipped with ballistic missiles, they formed the most survivable leg of the nuclear triad. Hidden in the deep, dark reaches of the world's oceans, they provided a constant, undetectable deterrent. They were capable of launching a devastating strike from anywhere on Earth. The oceans had become a vast, invisible nuclear battlefield. The nuclear submarine remains a testament to how the science of the atom transformed the very nature of global security. During the Cold War, nuclear weapons were tested repeatedly across the globe. More than 2,000 nuclear detonations occurred. From the remote islands of the Pacific to the vast deserts of Central Asia, the scale of testing was unprecedented. Some tests took place deep underground, vaporizing rock and creating massive subterranean cavities. Others exploded in the atmosphere, casting a blinding light across thousands of miles, or beneath the ocean. Colossal columns of radioactive water were sent into the sky, falling back as toxic rain. The explosions contaminated environments with radioactive fallout, invisible particles carried by the wind into the global food chain. Communities near testing sites often suffered long-term health consequences that persisted for generations. Pacific Island populations were displaced from their ancestral homes, which became uninhabitable for centuries. By the late 1950s, the human and environmental cost of these tests began to emerge. Desert regions, once pristine, became restricted zones of contamination marked by the deep scars of the nuclear age. As public concern grew and the global impact of radiation became undeniable, anti-nuclear movements expanded worldwide. In the Soviet Union, the massive Polygon test site left behind a landscape scarred by hundreds of artificial craters. The image of the mushroom cloud became a symbol of a planet under threat, fueling a global call for change. Scientists also warned about the possibility of nuclear winter, a global climate catastrophe triggered by large-scale nuclear war. They theorized that smoke from burning cities would block the sun, leading to mass starvation and the collapse of civilization. Eventually, the global outcry led to international treaties, such as the 1963 Partial Test Ban Treaty, which restricted atmospheric testing. Testing moved deep underground, hidden from the sky, but the process of detonation continued for decades. Today, structures like the new safe confinement at Chernobyl stand as permanent tombs containing the remnants of past disasters. The environmental legacy of nuclear weapons remains visible even today, in the isotopes found in our soil and the air we breathe. It is a permanent reminder of the extraordinary power we unleashed upon our own home and the responsibility we now carry. The future of nuclear physics depends not only on scientific discovery, but on wisdom. Humanity unlocked the nucleus. Now humanity must decide how that power will shape the future, as a source of destruction or a tool for healing and progress. The journey into the atomic world continues, but its ultimate destination is up to us. In the 21st century, nuclear security faces new challenges. Artificial intelligence and cyber warfare are transforming military systems. Modern nuclear arsenals rely on satellites, sensors, and advanced computer networks. Experts worry that cyber attacks or automated systems could increase risks during global crises. At the same time, artificial intelligence may also improve nuclear safety. AI systems can monitor reactors, detect threats, and analyze massive amounts of data faster than humans. The relationship between technology and nuclear weapons continues evolving, and once again, humanity faces difficult choices. How much power should machines control? Can advanced technology reduce the risk of catastrophe, or could it create new dangers? The future of nuclear physics may depend not only on science, but on the wisdom guiding it. From ancient philosophy to quantum mechanics, from glowing uranium salts to nuclear reactors and atomic bombs, the history of nuclear physics is one of humanity's greatest scientific journeys, a story of discovery, wonder, fear, and unimaginable power. And the story is far from over. Today, we stand at the threshold of a new understanding, guided by the lessons of the past. For thousands of years, humanity asked a single, profound question: what is everything made of? The journey to find the answer would become one of our greatest scientific adventures. From the philosophical atomos of ancient Greece to the birth of real scientific thinking in the 19th century, we slowly began to open the atom. J.J. Thompson's discovery of the electron proved the atom had structure. Ernest Rutherford reached the atom's dense heart, the nucleus. Soon after, the quantum revolution of Bohr, Heisenberg, and Schrödinger revealed a subatomic world governed by energy levels and probabilities. In the 1930s, we learned to split the atom. Nuclear fission released enormous energy and additional neutrons, creating the potential for a self-sustaining chain reaction. The implications were both extraordinary and terrifying. The secret race of the Manhattan Project gathered the world's greatest minds. On July 16, 1945, the Trinity test lit the New Mexico sky, and the nuclear age officially began. The atomic bombings of Hiroshima and Nagasaki ended World War II, but confronted humanity with the devastating reality of nuclear warfare, a permanent shift in global power and responsibility. The Cold War arms race brought the world to the edge of catastrophe during the Cuban Missile Crisis. Thermonuclear weapons, using the same fusion process that powers the sun, created unimaginable destructive potential. Yet, the atom also became a tool for healing and progress. Nuclear power plants light our cities, and radioactive isotopes save millions of lives through advanced medical imaging and cancer treatment. Sobering lessons from Chernobyl and Fukushima reminded us that this power demands extreme caution and global safety standards to protect our environment for future generations. Beyond Earth, nuclear energy powers our most distant probes and future space travel. At CERN, we continue to smash particles to uncover the deepest laws of the universe. Today, artificial intelligence and cyber warfare present new challenges and opportunities for security. The future of nuclear physics depends not just on discovery, but on the wisdom guiding it. The story of nuclear physics is the story of our journey to the heart of existence, a human story of curiosity, wonder, and unimaginable power. And the story is far from over.